In the theory of general relativity, Einstein's key assumption is that spacetime, a structure discovered in the theory of special relativity, spacetime therefore is curved. But how do we describe a curved spacetime by analogy with curved surfaces, which we presented in the previous episode? To clarify this point, today we will make an analogy with the spacetime of an ant that lives on a ring. Master the tape! Let's get started and build a simple model that describes the life of a one-dimensional being, an ant on a string, whose thickness is much smaller than the size of the ant. We will close the string in the shape of a circle so that it forms a ring and we obtain a one-dimensional space which represents the entire universe of the ant. Of course, the ant only sees its string, not what is inside the circle. At a later moment, let's widen the circle in the ant's world. The universe seems to be expanding because the length of the string will increase, the ant would say. Hey, it feels like I have more space to move around now. Now we'll take a picture, which we'll place over the picture of the previous situation, a little above it, like in a temporal stack, and then we'll continue the process. We enlarge the circle, take a picture and put it in the stack. At some point we can even shrink the radius of the circle and go back to a smaller circle. Towards the end, if we're bold, we can shrink the circle so much that it looks like a point. Now let's look at the trace left by the string ring. In the photos in the stack, we notice that we've built something similar to a sphere. Every horizontal plane that intersects the sphere is a circle. The perimeter of the circle, the ring, is the one-dimensional space where the ant is at that moment, its entire universe. The vertical dimension is limited. The ant can only see what's on the perimeter of the circle because it's on the one-dimensional thread, closed like a ring. The space of her time, which she can explore, is the surface of the sphere. The continuous horizontal lines, the lines of latitude, represent the ant's space at a given moment, while the dashed vertical lines, the meridians, represent the direction of time. Over time, the horizontal circles either grow or shrink, which means that the ant's space is dynamic. The chosen unit of measurement for distance in spacetime is the light year. It is measured with a clock or a ruler, the distance between the ants M and N. At rest, it is 5 light years here at first, because later it becomes 4 light years. Between O and A, since space has contracted along the world line, a clock travels between event A and event B. If time had been described by the Minkowski metric, by the analogy of flat surfaces, the proper time elapsed shown on the dial would have been 3 years. We saw this in the previous episode. Now, it would have a slightly different value because spacetime is curved. The question is what the answer is. Just the coordinates drawn in the figure are not enough. After all, these coordinates are arbitrary and can be chosen in another way. As I mentioned in the previous episode, the distance between 2 points, events, the relativistic interval in spacetime, is no longer given just by the difference in coordinates. Just like with curved surfaces, we also need an additional set of numbers. These additional numbers, different at each point and usually denoted by g, are called the metric. In this figure, I've illustrated the 3g numbers, which we consider approximately constant between a and b. In practice, the formula is used for very small distances. They represent the metric tensor of spacetime, associated with the particular coordinate system constructed. Of course, since we constructed the ant's spacetime, we also have to specify what this g-metric of spacetime actually is at each event in spacetime in the already chosen x and t coordinate system. To calculate the relativistic interval between a and b, the distance in spacetime, we need to use this formula here. Delta x is equal to xb minus xa. It's the difference between the xa and xb coordinates of the two events a and b. Similarly, delta t is the difference between their time coordinates. Next, gtt, gxi, and gxt equal to gtx are the 3 numbers that represent the metric in that area. Here is the exercise announcement with the previous formula. You can also calculate the relativistic interval between a and b. Here is my calculation from the narrated physics. I hope I didn't mess anything up and we all get the same result. I got a relativistic interval delta S of 2.44 light years. We notice that the value is positive and real, not imaginary, which means that the relativistic interval between A and B is temporal. A clock can travel along the shortest path between the two events, and its proper time will show 2.44 in the spacetime metric. It hides an unsuspected wealth. At first glance, primarily because the events are set on a spacetime structure, it means that we can calculate the relativistic delays of a clock, its proper time shown on the display, just by knowing the trajectory of the moving clock. Look, here is represented a curved world line, AD. The length of this curve in spacetime is calculated by breaking the curve into very small elementary segments. We don't need to take apart the components of the clock. We don't need to check the orbits of the moving electrons to calculate the clock's delays. The proper time of the clock is a direct measure of the length of the trajectory in spacetime. The clock is a kind of ruler of spacetime. The clock carries within it a trace not only of time, but also of the space it has traversed. And since the lengths of the trajectories through spacetime can be different, two clocks will also show different times. You see, even if they start next to each other and meet again later, look here, two synchronized clocks leave from the same event A and meet again later at B. On the dial of the clock on the left, 1 hour has passed, so it has covered a distance of 1 hour. The one on the right shows that 6 hours have passed, so it has covered 6 hours. Light in spacetime. We notice how the distance in spacetime is counterintuitive compared to our sketch, because it is greater for the temporal segment on the right, which appears smaller in the figure. We also notice that the clocks show different times at the end, even though they started with the same reading at the beginning. Of course, neither of the clocks is broken. It's just that they follow different paths in spacetime, and therefore they experience different relativistic delays. What happens in our spacetime, which has 4 dimensions, 1 of time and 3 of space? Of course, we can't directly visualize something like that, but we don't give up because we have calculation formulas, and in our minds we make analogies to solve practical problems. Black holes, planets around massive stars, and others. We need to mathematically define 2 things. A coordinate system x, defined arbitrarily on the right side, and the metric g in this coordinate system on the left side. The metric will now be a 4x4 matrix different at every event in spacetime. If spacetime is not curved, the metric g reduces to the Minkowski metric. Next, to calculate the relativistic interval, we need to use the already known formula, generalized to 4 dimensions, t, x, y, and z. That's why we have the sum from 0 to 3, a total of 4. This is the mathematical framework. Of course, there are many books that explain it in detail. The one that helped me the most was the book Gravity by James Hartler. In the end, let's say that our example with the ant is just an analogy and should be treated as such. I am highlighting the key points. The coordinate system chosen at the beginning is arbitrary for our ant. We chose to draw the events on a sphere, but we could just as well have drawn them on the surface of a potato. It didn't matter anyway. What matters is only the metric g associated with the chosen coordinate system, because it gives us the relativistic interval, the one measured in light years. Check using a ruler or the proper time of the clocks. I like this model, which I'll show here once again because it highlights other things as well. Here, for example, the world lines of some atoms in this universe are drawn. Lengths in spacetime are measured with a tape measure placed between any 2 events in spacetime. This tape measure, however, represents either a ruler or the world line of a clock. The reading of the tape measure in the second case is the proper time of the clock. Here, space is dynamic, expanding and contracting over time. The model is an analogy with our universe after the Big Bang, when it appears to have expanded, as we will see later. There is one more hidden ingredient in this model, the beginning and end of time itself. Let us note that the ant's ring, its entire universe, disappears into nothingness once it has been reduced to a point. We see how time itself ends at that same moment, something that could also happen to our universe. A possible big crunch, in other words, the end of time at the north pole of the ant's spacetime sphere, is a very good analogy for the end of our own time at the big crunch. The same analogy applies to the creation of time at the Big Bang. How can time be created? How can it end? These are some of the great mysteries of knowledge. The creation of time seems unimaginable to us, and infinite time is no easier to imagine because it seems that emotions would reach saturation at some point. If we lived forever, eternal boredom would set in. Up to this point, today and in the future, we have to answer two fundamental questions. The first refers to the way objects move when left free, or the path followed by a ray of light. The first principle of mechanics states that a body on which nothing acts moves in a straight line and at a constant speed. Straight in our space, which is now curved, what does straight mean? How will that body move? The second question is, who determines the curved structure of spacetime? In the case of the ant, we are the ones who actually built the spacetime, but in our case, who determined the metric structure of the four-dimensional spacetime in which we live? Another creator? If not a creator, then who? Hey, there are still many things to find out until next time. Please subscribe, if you haven't done it yet, by clicking this subscribe button right now. I want to thank those who support us on Patreon and those who become channel members here. I am Christian Presura, Physics Explained. You are cool, and I wish you all the best. Goodbye.